So, last time we learned what a graph is. It is just a group of nodes and edges. But now comes the real question. A computer cannot see your city map. It cannot see your friend network. So how do we actually store all these connections inside the code? How do we tell the computer this node is connected to that node? Today, we crack the first way of doing it. It is called the adjacency matrix. Do not worry about that big name. By the end of this video, it is going to feel like the most obvious thing in the world. Let me start with something you have definitely seen. A distance chart, like the ones at the back of an old atlas. The same cities are listed across the top and the same cities down the side. To find the distance between two cities, say Delhi and Mumbai, you pick Delhi's row, slide across to Mumbai's column, and the box where they meet gives you the distance. That grid? That is basically an adjacency matrix. Let us build it slowly. Imagine we have 4 friends. Let us call them 0, 1, 2, and 3. Now we draw a grid, 4 rows and 4 columns. The rows are our friends 0, 1, 2, 3 going down, and the columns are the same 4 friends going across. So every little box in this grid sits at a crossing, a row friend and a column friend. And that box answers one simple yes or no question. Is this row friend connected to this column friend? If yes, we put a 1 in the box. If no, we put a 0. That is the entire idea. 1 means connected. 0 means not connected. Let me make it real. Say friend 0 is connected to friend 1. So we go to row 0, move across to column 1, and we write a 1 there. And because this is an undirected graph, friend 1 is also connected to friend 0. So we go to row 1, column 0, and put a 1 there as well. 1 connection, 2 boxes. Next, friend 0 is also connected to friend 2. Same simple steps. Row 0, column 2, write a 1. And its mirror, row 2, column 0, gets a 1 as well. And friend 2 is connected to friend 3. Row 2, column 3, a 1. Then row 3, column 2, its mirror, another 1. Notice we are filling 2 boxes for every single connection. Now step back and look at the whole grid. Every 1 we wrote on this side of the diagonal has a perfect twin on the other side. The grid has become a mirror. For an undirected graph, the matrix is always symmetric. And if it were a directed graph, like following someone on Instagram, we would put a 1 in only one box, not both. The mirror would break. That is how the grid quietly remembers the direction. So just by filling this grid with zeros and ones, we have captured the entire graph. Every connection stored neatly in a table. Now let us see this in actual Java code. And trust me, it is shorter than you think. In Java, this grid is simply a 2-dimensional array. Picture it as a table with rows and columns, exactly the grid we just drew. We first decide how many nodes we have. Let us say 4. Then we create a 4x4 integer array. The moment we create it in Java, every single box automatically starts at 0, which is perfect because 0 already means not connected. So our empty graph is ready without any extra work. Now to add a connection between 2 friends, say friend A and friend B, we do something very simple. We set the box at row A, column B to 1. And because this is an undirected graph, we also set the box at row B, column A to 1. 2 small lines, and the connection is stored in both directions. And if we ever want to check, are these 2 friends connected? We just look at one box. We go to row A, column B, and see if it holds a 1 or a 0. 1 means yes, 0 means no. And here is the best part. Looking up any box in a grid is instant. It does not matter if you have 10 friends or 10,000. Checking a single box takes the same tiny amount of time. That is the superpower of the adjacency matrix. But, and there is always a but in DSA, this convenience is not free. Think about it. If we have 1000 nodes, we need a grid of 1000 by 1000. That is 1 million boxes. Even if barely anyone is connected, we are still reserving space for every single possible connection. Most of those boxes will just sit there, holding zeros, doing nothing, eating up memory. So here is the honest trade-off. The adjacency matrix is brilliant when your graph is small, or when it is dense, meaning most nodes are connected to most other nodes. Checking a connection is lightning fast. But if your graph is huge and sparse, lots of nodes, very few connections, it wastes a lot of space. Let us quickly bring it all together. An adjacency matrix is just a grid. Rows are nodes, columns are nodes. A 1 means connected. A 0 means not connected. For an undirected graph, the grid is a symmetric mirror. Checking any connection is instant, but it can waste memory when the graph is big and mostly empty. And that is it. You now understand the adjacency matrix completely. Not as some scary term from a textbook, but as a simple yes or no grid. Next time, we will look at the second way to store a graph, the adjacency list. It fixes exactly this memory problem we just talked about. And for most real-world graphs, like your social network, it is actually the smarter choice. We will see why. So, see you there.